Hello, my voice there's some degradation to my voice since yesterday, but nevertheless, chirality part 2. I will try to be more robust than I sound. Today we'll focus on crystallographic considerations of chirality because that's where I spend most of my time looking at crystals. And then we'll also talk a little bit about braids at the end. Braids are wonderful structures that are connected to knots in a neat way and curiously emerge out of some crystallization experiments we're doing, or I hope they emerge out of some crystallization experiments that we are doing. In any case, okay, I just can't really address this. In any case, yesterday we had closed with the notion that it was Lord Kelvin's attempt to reckon with the periodic table of elements that ultimately gave birth to knot theory. His notion that they were knots tied in the luminiferous ether might account for the diversity of the chemical elements, and this led his pal Peter Tate to try to enumerate knots, and that is the origins of knot theory. But there's something that Kelvin is even more well known for, and that is the fact that he coined the term chiral because he was showing off the Greek that he studied in school. And so he said, I call any geometrical figure or group of points chiral and say it has chirality if its image in a plane mirror, ideally realized, cannot be brought to coincide with itself. And this is quoted by so many people over and over and over and over again that Lord Kelvin coined the term chirality. However, it didn't catch on. Nobody used it. So if you look at a Google engram of the frequency of the use of chirality when he introduced it in the Baltimore lectures in 1884, which were published in 1904, nobody used the term chirality until much, much later. But everybody says that Kelvin came up with this. In fact, chirality didn't start to get used until my PhD advisor, Kurt Mislow, proposed it in a letter to his good buddy, the natural products chemist Carl Jurassic, in a letter from 1961. And from that time on, chirality became part of everyday usage, but only from this letter in 1961. Now, you know what else happened in 1961 in October? I was born. So I am as old as the use of chirality, which seems really, really old. How can you be older than chirality? So if you were to integrate chirality between 1961 and the present, then you come up with me. How can you be as old as chirality? It's kind of shocking. But you can be older than chirality because, well, after all, I'm the only person on this page who is still with us. So you can be older than the contemporary use of chirality, although it's a sobering thing to think about. But nevertheless, people knew about chirality long before Mislow and long before Kelvin. And we get back to our good friend Pasteur, who will be a touchstone throughout. And Pasteur never used the word chirality. Instead, he used the word dissymmetry. He said, look, I see some crystals I made, and they're enantiomorphous, they're chiral, they're dissymmetry. I see left-handed ones, I see right-handed ones. His genius was to separate the right-handed ones from the left-handed ones dissolve them, make them disappear, and then show that solutions scattered left and right circularly polarized light differently. And this was a momentous discovery, because he says, I can no longer see the molecules, but I know that they too must be dissymmetry, and their dissymmetry has to be correlated from the crystals that they came from. And this was the first time that anyone had correlated macroscopic chirality, things that you can hold in your hand and turn around and touch, with microscopic chirality, the actions of molecules on polarized light, the actions of molecules that you cannot see. And from this, Pasteur deduced that the arrangements of the atoms in those molecules likewise had to be as object and mirror image. He didn't really know what the structure was. He didn't know where to put the atoms, but he knew that they had to come as object and mirror image. And so this was the first time we learned anything about the arrangements of atoms in space. And that is why this is such an important experiment that we'll return to time and time again. Now, my PhD advisor, this fellow, Kurt Mislow, I just showed you, who reintroduced the word chirality. I also showed you this funny molecule that he made yesterday, this amphichiral molecule, a molecule that can turn from object to its mirror image, but without ever going through an achiral transition structure. And he made this in 1955. Oddly, he made it at New York University, which is the same place I work today. But in 1955, he wasn't talking like himself or like I knew him to talk. He was talking like Pasteur. He never mentions chiral or chirality. It's all dissymmetry, 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 because I had not yet been born, which prompted him to coin or recoin the term chirality. So before inventing microbiology and the germ theory of disease, Pasteur was a young and humble crystallographer. He wasn't actually ever that humble about anything. He had extraordinary confidence. But that's what he did. He studied crystals. And what was known about crystals in 1848? Well, we knew from Auguste Bravais about the crystallographic systems, triclinic that has no orthogonal basis vectors, and monoclinic and orthorhombic and so on, and the systems of point lattices. That's what Pasteur was familiar with. He didn't really have a fulsome understanding of crystal symmetry in 1848. It turns out that there was a mineralogist, Johann Hessel, who had recognized that crystals could have 32 different point symmetries, 32 different point groups. And he recognized that 11 of those were chiral. And this is Pasteur's crystal up here, symmetry C2. However, Hessel's work was completely overlooked until the late 1890s. And so he made a big, he had a big insight here, but it wasn't appreciated at the time. The big leap came in 1890 when the space groups for crystals were enumerated by Fedorov and Schoenflies. And the space group is a translationally repeating pattern of some asymmetric motif in 3 non-parallel directions in a semi-infinite way. Semi-infinite meaning it goes on and on and on, but not forever. I mean, crystals they have edges eventually. But compared to the size of molecules, they're semi-infinite. And they figured out that there were 230 such space groups. What do I mean by an asymmetric object? Well, I mean some object that has no symmetry, like a chiral molecule or a potato. A potato is a very nice asymmetric object. A potato has no symmetry. There's something wrong with every potato. The bent here, it's got an eye here, and every potato is asymmetric. And they figured out, what you could do with potatoes in space. You could translate a potato this way or that way. You could rotate a potato. You could reflect a potato. You could combine rotations of potatoes with translation. So this potato is rotating, but it's also screwing out towards us. So that's why the potato is getting bigger as it rotates around this helix. Or you can combine rotations and reflections. You can glide a little bit and then hop over a mirror plane. Glide a little bit, hop back over a mirror plane. And they recognize that by combining these possibilities, you could make 230 groups, 230 groups of operations that conform to the 4 necessary axioms of any group in group theory. 230, that's what they came up with. And I think that this is one of the greatest systematic achievements of geometric thinking in all of history. Because 230 is a lot. Now, when you say something is a lot, that doesn't mean much. Compared to what? 230 is a lot. Compared to what? Well, compared to push-ups. Like, it turns out in 2 dimensions, there are only 17 crystallographic groups or plane groups, the so-called wallpaper groups. But when you, and Fedorov proved that there were 17 plane groups before he proved that there were 230 space groups. So he went from 17 to 230. Now I can jump out of bed on any morning and do 17 push-ups, but I can't do 230, no way. So compared to push-ups, 230 is a lot. Compared to remembering the names of students, I can remember the 17 names of the students in my graduate class, no problem. But the 230 names in my undergraduate class, no way, right? Big difference between 17 and 230. But they were able to make this, jump this chasm in a way which I find to be truly impressive. So they enumerated the 230 space groups for crystals. Why only 230? And not some other number? And why is there a limit? I'm combining rotations, reflections, translations and rotations, and translations and reflections. Why is there a limit? The limit comes from something called the crystallographic restriction. So let's say you have a line of lattice points, say lattice points A, and you want to make some new lattice points, and you want to make those new lattice points by rotating the blue points to some other direction by some angle theta, and then you want to make some more lattice points by rotating by theta again to make the yellow lattice points. It has to be the case that the new points that you make ultimately have to be separated by some integral number of lattice constants. Because if they're not, they won't be lattice points, and then they can't be points in the lattice. And if you work out the trigonometry, m must be an integer, and it can only be 1, 2, 3, 4, or 6, so that you can have allowed rotations of 360, 180, 120, 60, 90, or some other number which I left out. I think I left out some number in the series. 360, 180, 120, 90, and 60. All the only rotations that are allowed, and that's why there are a finite number of space groups. Now, of those 230 space groups, Fedorov and Schoenflies, they recognized that some were chiral and some were not chiral. There were 165 of those 230 that had at least one symmetry operation of the second kind that rendered them achiral. But there were 22 space groups that came in 11 mirror image pairs that were chiral. And the chiral space groups have the characteristics of a screw. So these are symmetry operations that are screw axes. So if you start with a point at position X, Y, Z, and you rotate it clockwise around an axis by 90 degrees, and then each time translating a quarter along Z, you ultimately end up with a right-handed screw. And you can do the same thing by rotating anti-clockwise, as we were forced to do last evening, and then you're gonna end up with an enantiomorphous screw P43. And so P, if force of 1 and force of 3, these are enantiomorphous symmetry operations in a space group. But I told you that there's some chiral space groups and some achiral space groups, 165 of one kind and 165 of another. But 165 and 22 don't add up to 230. What about the rest of them? And the rest of them belong to another class. These are 43 space groups that are not themselves chiral, but they support chiral crystal structures. And this is a subtle point that is often confused. And so there are some groups that, despite the absence of reflection symmetries, groups that just have rotation axes or screw axes, these groups themselves are achiral, yet they're characterized by crystals that are chiral. And when we add these 43 space groups to the 22 space groups, we get the 65 so-called Sanka groups that can support chiral crystals. And the reason why there are some space groups that are achiral that support chiral crystals is the fact that some screw operations have no sense. So if I have a 2 sub 1 screw axis, that means I have to rotate by 2 pi over 2 and translate by a half along the lattice constant. And so that means I have to go from point X, Y, Z to some other point over here, where I change the sign of X, I change the sign of Z, and I translate a half and Y. But there's 2 ways that I can get from here to here. I can rotate clockwise, or I can rotate counterclockwise. I get to the same place. We would have gotten to the same place if we had rotated our teacups in either way, but there are traditions that we couldn't violate. Here, you can go clockwise, you can go clockwise, it doesn't matter which sense, you get to the same point. So as long as you're thinking about a lattice of points, P21 is an achiral space group. But once you decorate it with chiral atoms, then the crystal becomes chiral, and it supports mirror image crystals. So we can have a crystal that is made out of right hands, boom, 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 that's P21, or we can have a crystal that's made out of left hands, boom, 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 it's also P21. No problem, and enantiomorphous groups, but they have the same space group. It's a curious thing. People very frequently say that, P21 is a chiral space group, but that's a misnomer. What they really mean is that it can support chiral crystals. And here are the chiral point groups that just have proper rotations, and the chiral or Sanka crystals that are correlated with the point symmetries. 11 out of the 32 are chiral. And of the space groups, 65 out of the 230 are consistent with chiral crystals. Yes.
So going back to the hands in the P21 case, I guess not knowing about crystallography, how do you know what subsets of atoms should be considered as a point when deciding on the symmetry, and then what's extra sort of decoration?
So, well, if the hands are groups of atoms, then we could analyze by X-ray scattering the scattering of X-rays from these two crystals. And it turns out it would be very difficult to distinguish one from the other, just because there's not a profound difference between the scattering of crystals that only differ in their handedness, because the scattering pattern is projected. It's projected onto a plane. And so you lose a lot of the three-dimensional information when you want to distinguish between the enantiomorphs. And what's required is that you use a wavelength that is close to the absorption band of the X-ray radiation that you're using, so that you get a small contribution to the scattering factors of anomalous dispersion. That is, you begin to catch an absorption band when you do the inelastic scattering of X-rays from crystals, and that can allow you to differentiate the scattering of right and left hand, but it's a subtle thing. It relies on something called the breakdown of Friedel's law. The Friedel's law says that the scattering of reflections for mirror image crystals are the same in the absence of anomalous scattering. And so you have to then add to it, you have to add an imaginary term to the scattering in order to be able to distinguish right-handed things from left-handed things. It's actually kind of tough. Distinguishing between left and right chemically is really absolutely is a very hard thing to do. Distinguishing between right and left in chemistry is very hard to do. Distinguishing between right and chemistry relatively is fairly easy to do, but absolutely, then we get to the problem of, can you communicate to an intelligent being on planet X? And then it becomes a whole can of worms. I don't know if that helped answer your question. It's interesting. So a lot of people get a lot of joy out of crystals. And some people think they get health and clarity of thinking from crystals as well. And so there's lots of books about crystals. And they all sort of brag about how many crystals that they discuss in their various books, 100, 1,001, 500, 180. And curiously, they're all kind of in the right ballpark. But if you really want to talk about what's fundamentally different between one crystal and another, the number, of course, is 230, because the number of different groups of any system is as fundamental a distinction as you can possibly make. And so I go back to this beautiful quote from the mathematician Hermann Weyl. He said, this letter, and he's talking about the letter in which Evariste Galois invented group theory the night before he perished in a duel. And he said, this letter, if judged by the novelty and profundity of ideas it contains, is perhaps the most substantial piece of writing in the whole literature of mankind. That's a good review. My soul is an amphichiral knot, maybe is a close second in the literature of humankind. But it's the symmetries which are the most fundamentally different things that you can have for any group of objects. And nobody knows that 230 is really the number that they ought to be talking about, not these other numbers that are within a factor of 5 and are arbitrarily chosen. So we started with the periodic table of knots. Here's the periodic table of elements. There's about 100 elements, rounding to the nearest 100. There's 118 now that goes through organism. But everybody knows something about the periodic table of elements because everybody went to middle school and there was a periodic table hanging on the wall. And so even if you don't know a lot about it, you know something about the periodic table of elements. Your brothers and sisters know something about it, or your parents know something about it. Even if they all hated, chemistry, they all know something about how matter is organized by the periodic table of elements. Now, in terms of space groups, there's about 200, rounding to the nearest 100. And nobody really knows that this is how space is very generally decorated by matter. So this is how matter is organized in the periodic table. But then you have to do something with that matter. You have to use it to decorate space. And most things, when you cool them, become crystalline, and they adopt one of the 230 Fedorov-Shonsky space groups. That's a really fundamental thing about how matter is organized in their world. Now, Mendeleev knew about 60 elements, and he predicted the positions of 4 more. Good for him. Fedorov and Schoenflies, in 1890, they had 0 crystal structures. Nobody knew what a crystal structure was, but they predicted all 230 possibilities de novo. They went not from 60 to 64, but from 0 to 230 in one shot. But there is no periodic-like table of space groups that you can hang in a classroom. So nobody really knows that 230 is the number that ought to be described. And this year I was asked to write something for a special issue of Crystallographic that was devoted to crystallography education. And I thought, I don't have anything to say about crystallography education, but then I thought, well, maybe I should invent the periodic-like table of space groups that you can hang on the wall. Maybe that will serve to raise 230 above the din of the other arbitrary numbers that are applied to crystals. And so this is what I made. Periodic table, periodic-like table of space groups. And what I did is I made a table that was organized along 2 axes that ran along a diagonal. On the left axis was the point symmetry of the crystal that determines its physical properties by the Naumann-Curie symmetry principle. Physical properties are determined by the symmetry. And on the right side, I plotted the periodicity. And the periodicity is the number of potatoes you would need to fully illustrate the symmetry of that group. And so for some groups, you just need 1 potato. Some groups you need 8 potatoes. Way down here, you would need 192 potatoes to fully illustrate the symmetry of the group. And that's what I came up with. And well, in the absence of this, what do we have? We have this big giant book, which is almost 1,000 pages long, which describes all of these groups, and you have to go through it like a book linearly. And so I set myself the task of, well, if you had to boil this giant book down to 1 page and hang it on the wall, it would look like this. And what very neatly happens is when you plot it this way, you end up with the individual crystallographic systems separated into color fields, kind of like the metals and non-metals and noble gases that you see in the colored periodic table of the elements. So I'm on a mission. I'm on a mission to promote 230 as a very special and important natural number.
How does this label it? What are all the M's?
What are all the these little, so these are the notations. It's a shorthand that indicates what the symmetries of the space groups are, and it's sort of a language that you have to practice, but it's just jargon, is what it is, really all it is. It's just jargon. I mean, some of them are easy, like F222. That means that the lattice is face-centered. Every face has a point in the center, and there is a 2-fold axis along each orthogonal direction. Some of them are easy to narrate, and some of them it takes a little bit more practice. But it's just jargon. But here's the thing about it. Fedorov and Schoenflies predicted these 230 possibilities. And now we know more than 1 million different crystal structures. We know where the atoms are in more than 1 million crystal structures. And it turns out that they made a prediction that every crystal was going to occupy one of their 230 groups. And they were proved right 1 million times in a row. That's good work, right? Imagine making a fulsome prediction and then being proved right 1 million times in a row, time after time after time after time. How could you do more robust science than that? Let me tell you 2 little stories. So there were some scientists who found some frozen carcasses of extinct woolly mammoths. And they extracted the DNA, and they expressed the DNA in E. coli, and they made the hemoglobin, and they crystallized it, and they determined the crystal structure, and it crystallized in the very first Fedorov-Schoenflies group P1, has just translational symmetry. Boom. Fedorov-Schoenflies. What did they know about DNA? Nothing. Did they know of anything about proteins? Nothing. But eventually, somebody expressed woolly mammoth hemoglobin and had to fall into one of their space groups. Here's polonium. Polonium was discovered by Marie Curie before radium. It's a radioactive element, and it has a really weird structure. Because in the polonium crystal structure, you get a simple cubic structure where the spheres are sitting right on top of other spheres. And that's absolutely pathological because spheres like to be close packed. Spheres don't like to sit right on top of other spheres. They like to fit between neighboring spheres and be close packed. They like to be face-centered cubic or hexagonal closest packed. Simple cubic packing is absolutely weird. And the only way that you can account for this structure is by considering relativistic effects on the wave functions of the polonium atoms. Fedorov and Schoenflies, they didn't know about radioactivity. They surely didn't know about special relativity. But when polonium was crystallized, had to be in more than 230 space groups. Boom, it was 225. Predicted the future like nobody else. I really love these guys. They did really high class geometric thinking before their time. But there's always a but in any good story. There's a but, and the but is that this restriction is overwrought. And it's become some kind of a tyranny. So I had a friend who recently passed away, Jack Dunnins. He was 98 years old, and there was a special memorial issue for Jack. He wrote a paper called Chiral Crystals, Jack, Conductivity, and Magnetism. And in the last section of the paper, we asked, can any crystal made out of molecules be chiral? And I just answered that for you in a very complete way. The answer is no. No way. Fedorov and Schoenflies said 165 out of the 230 groups are not chiral. So no. What makes me think this? Well, you go back to Pasteur. Everything begins with Pasteur. Pasteur had these antimorphous crystals, and he recognized that there were these hemihedral facets that rendered the otherwise symmetrical crystals mirror images of one another. And in the subsequent generations, people have just gone on and on and on about these so-called hemihedral faces in Pasteur's crystals. Blah, 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 chirality, Pasteur, yay, look at these crystals. Enough already. I've seen the movie. Stop talking about it. You wouldn't believe how many papers about the chirality of this molecule or that molecule begin with the phrase, ever since Pasteur, It is the most tiresome. In fact, Jack Dunnett's had a rule, and the Dunnett's rule was this. If you delete the first sentence of every paper, that paper gets better. And that's almost certainly true. And so anytime you read ever since Pasteur at the beginning of the paper, just skip straight to the next sentence. Why the excitement here? Because in 1832, Justus von Liebig and Friedrich Rohler, two German organic chemists, crystallized benzamide, simple molecule from hot water, and it crystallized as helicoids. And these crystals, it's not that they have a couple of little faces that are evidence of their dissymmetry, but the entire surface has curvature. The entire surface is evidence of their dissymmetry. Why are we talking about these tiny little faces on these polyhedra when you can take benzamide, crystallize it from hot water, and get helicoids? And in fairness to Pasteur, he didn't know about this because we only described these crystals in 2020. And in fact, Liebig and Wohler, while they could have seen this with an optical microscope, they didn't look. And they didn't look because Liebig and Wohler did not believe that microscopy had anything to teach a chemist. And I know this because Liebig's lab is preserved as a museum in Gießen. Well, it was until it burned down, but I visited it before it burned down. And Liebig more or less invented organic chemistry out of whole cloth because he perfected combustion analysis. If you want organic chemistry to be a science, you have to be able to separate this gooey hydrocarbon from this gooey hydrocarbon. So you really have to be accurate about distinguishing the compositions of things that are made mostly out of carbon and hydrogen. And he perfected that, and his lab was filled with beautiful, sophisticated analytical balances, but there were no microscopes there. And in fact, you don't have to believe my retrospective visit to his museum, because he said how much he reviled microscopists and microscopy. He had his own journal, so he could say anything. And well, here I am with Liebig. I probably shouldn't have been so affectionate with him in a museum, but there's the evidence. But in any case, he made a satire about scientists like Pasteur, who thought that animals had something to do with fermentation. And he wrote in his satire, he can see under the microscope the little animalcules chewing on the sugar, and the CO2 is coming out their genitals, and the ethanol is coming out their anus, which is not terribly sophisticated satire for such a smart guy. But that's what he thought of microscopists and microscopy, because he just didn't believe that animals were involved in fermentation. We know, of course, how this story turned out. Pasteur clearly won this debate. But in any case, Pasteur even himself could have seen much more dissymmetric crystals like this. So he made his big leap into scientific immortality with his salts of tartaric acid in 1848, and he wanted to repeat this magic with something else. And so he chose a very similar molecule, malic acid, which comes from apples. And he said that he had isolated both racemic malic acid, a mixture of right and left, and also the optically pure malic acid. And he described how he determined their melting points, quite like you would take a melting point in an organic chemistry laboratory at a university. You put a little bit of stuff in a tube and put it next to a thermometer and an oil bath and measure the temperature at which something melts, which is characteristic. The thing of it is that Pasteur never looked at his melted crystals, because at that time, nobody had invented a hot stage for a microscope. So Pasteur never looked at his melted crystals. But if he had looked at his melted crystals, he would have seen malic acid that looks like this. He would have seen a radial aggregate of crystals, fine fibrils, growing from a common nucleus. And along the radii, he would have seen a precession of the refractivity, which was manifest in the contrast that was seen in the petrographic microscope. And so he got alternating light and dark bands. And the only way he could possibly have interpreted this is if the crystals, as they were growing radially, they were twisting helicoidally, so that the refractivity of the object was processing in a rhythmic and regular way. He could have been well on the way to a generalization of crystal form 150 years sooner than it took to really get on this track, if he had looked at his melted crystals. Now, occasionally, you can see individual helicoids of simple organic molecules, but generally, they tend to pack as tight radial fibrils, so you get these bullseye patterns, which are not unfamiliar to folks who study cholesteric liquid crystals, for example. But these are not liquid crystals, these are bona fide crystals that give X-ray counter diffraction patterns of the normal crystalline phases that under ordinary circumstances would have polyhedral forms. And this is so common that we can do it with just about any molecule. So 30 to 40% of just the random molecular compounds that we have in our lab, we can grow under some conditions that will force the crystals to grow with a helicoidal twist. Most common thing in the world that I didn't know about until recently. And this presented us with a real problem. Because if this is such a common thing, helicoids are not polyhedral. So why are so many crystals twisted? I learned that a crystal has some basis vectors. Basis vectors progress with semi-infinite translational symmetry. That lattice gets terminated by planes, which leads to flat faces and sharp edges and polyhedra. And that's what's so lovely about crystals, because things with flat faces and sharp edges are so unlike everything else in nature. That's why so many people think that they're magical and that they can bring you health and wisdom and all kinds of other benefits. And this is what I learned, and I studied crystals for many years. But when it turned about 50 or so, all the straight crystals that I was familiar with just all started twisting up on me. And it was the strangest thing. How can it be that something that you study so closely for a long time completely changes underfoot? That's a crisis. First of all, you have to explain, how can it be that you didn't know what you were looking at for the longest time, or you were looking in the wrong place? But it's also a wonderful thing, because whenever things change underfoot, that's a privilege, because if everything stayed the same, then science would be a lot less fun. And so we had to reckon with the fact that what I always thought was straight was now fundamentally not straight. So here's a molecule. There's a lot of molecules. So let's say there's some molecule that's going to satisfy the precondition that I'm about to establish. Say this is a molecule and it likes to associate with itself by rotating by 57 degrees. And we can do that operation 6 times. And when we get to the end, we end up with a hand that's not quite the hand that we started with. We end up with a hand that defines a 6.3 sub 1 screw axis. But there's no such beast in crystallography. There's no such rotation. It's got to be 60 degrees from end to end. Can't be something partial. And so this kind of object, it can associate with itself and it can grow a little bit, but it can't become a crystal because of the crystallographic restriction. There is no such 6.3 screw axis. It can end up as being some kind of organized nanoscopic thing, like an amyloid fibril, if you know what that is. If you don't know what an amyloid fibril is, there's a nice poster by Shinichi Tate. Is she Tate?
He's
Okay.
attended over Zoom. Yeah.
He's attending over
Have
Zoom.
a meet today, so.
Okay, so in any case, if you don't know what an amyloid fibril is, on the wall on the post, you can find an amyloid fibril. An amyloid fibril is a nanoscopic twisted thing, and they're size limited. They can't grow. They can't grow because they can't untwist. If you want a crystal to grow, then the molecules have to twist a little bit more. You get a proper 6-fold screw axis. And once that happens, then according to Fedorov and Schoenflies, you can grow these things as big as you want. You can grow and grow and grow and grow, but you must conform. And that has a cost. And that cost is the cost of some strain. If the crystals, though, are slender enough, this strain can be relieved by undergoing a whole body mechanical deformation, only if the crystals are smallish. And for the kinds of crystals that I've been showing you in these rhythmic spherulites, it turns out that it doesn't take a lot of energy to twist them. This is the elastic energy to twist the rod. You can get this formula out of any book on continuum mechanics, but it's more or less like a Hooke's law formula that depends upon the square of the twisting angle, but it also depends upon the fourth power of the cross-sectional radius. So that means it's easy to twist a nylon thread, but it's very hard to twist a 2x4. Elastic energy goes as the fourth power of the radius. The fact that this happens all the time, I'll give you 4 pieces of evidence. One is that pitch and thickness are correlated over 5 orders of magnitude in thickness. We can watch crystals untwist as they thicken. And so here's a crystal that's twisting at the tip where it's narrowest. But as the crystal begins to get fatter and fatter at the older part, it begins to pack on new elastic forces, which drive the twist back toward the tip and expel what's happening at the tip. And so at the tip where the crystal is very fine, you're twisting the lattice by 2 pi radians, multiples thereof. But as the crystal gets fatter on the back end, it's expelling the previous twist towards the tip. We can watch this with our eyes. We can do experimental math. We can take helicoids glued out of silicone with a prescribed pitch, and then we can glue them together. If we glue 4 of them together, the pitch is expelled as the square of the radius. If we glue 16 of them together, the pitch is expelled as the square of the radius. The exact same thing happens in molecular dynamic simulations. Narrow crystals are twisted. Thick crystals, the pitch is expelled as the square of the radius. And this leads me to some really interesting, an interesting new outlook about crystal form. Slender crystals can eliminate stress associated with the space group restriction by undergoing whole body mechanical deformations. But if crystals want to grow, they have to straighten out. It's like an unruly kid. Ultimately has to follow the rules. Gotta straighten up. And that leads to the conclusion that many straight crystals, things that I took as axiomatic, are actually artifacts of growth. The reason many crystals are straight is not because they are straight in principle, but it is because they cannot take advantage of the thermodynamic driving force of growth unless they straighten out. And that's a completely different way of looking at the crystalline state in my view. So here's a crystal of quartz, and it's kind of a big crystal, 15 millimeters. And if I had this crystal and I tried to twist it, it would be really hard to do. I couldn't. But that's because this crystal is already big and already straight. It must therefore mean that if we could find some fibrous quartz somewhere, it ought not be straight. And indeed, you can find chalcedony, which is a fibrous form of naturally occurring quartz, and it looks just like malic acid or all of our other crazy crystals that have fine radial helicoidal fibrils that are packed tightly together. And this can happen because the crystals aren't big yet. Okay, so I told you we keep going back to Pasteur. Pasteur couldn't distinguish his transparent crystals directly by optical activity. You may wonder, oh, look, he's got transparent crystals. He's interested in how they scatter circularly polarized light. Why did he bother dissolving his crystals after the hard work of separating the right-handed ones from the left-handed ones? Why didn't he just make the measurements straight away? And he couldn't measure this straight away because he didn't have, at the time, accurate photometry, and he didn't have digital computers. He just lived too long ago. However, maybe we can do what Pasteur could never do. That is, assign optically the handedness of a dissymmetric crystal along a low symmetry direction by directly making some kind of polarimetric measurement. This is paracetamol growing from the melt. Fantastic crystals, certainly not straight needles. And we analyze these with the so-called polarization transfer matrix microscope. This is a microscope that modulates some input polarization and simultaneously modulates the output polarization at a different frequency, which gives rise to a time-dependent intensity signal, which can be subject to a Fourier analysis, which can then separate out various physical contributions to the psychedelia that you often see when you look in a polarized light microscope. And so if we look at these crystals and we measure the linear retardance, this is a quantitative micrograph that's proportional to the difference in refractive index for light polarized in orthogonal directions. We can see these twisted fibrils, no problem. But this is a kind of an easy data to get because this is a really big effect. This is kind of like 19th century data. But this is 21st century data. This is the circular retardance separated from the retardance as a whole, which allows us to distinguish very clearly the right-handed twisted crystals from the left-handed twisted crystals without dissolving anything. We can see it straight away. And the reason why this is such a hard thing to do is that the linear retardance, the difference in refraction for orthogonal polarizations, can be 1,000 times bigger than the difference in refractive index for left and right circularly polarized light. So if you're interested in this effect that was so important to Pasteur, that led to our first understanding of the arrangements of atoms in space, if that's the quantity that you're interested in, then the only way you can usually see that is if this is zero, and that's if, when this is zero, only if you dissolve your crystals. But if this is big and this is small, then you really have to make accurate intensity measurements if you're going to be able to separate out a small thing from a big thing. And so this is the experiment that Pasteur would have done if he could have done it 175 years on. Most things in science don't take that long. When we work together, we're really good at science when we work together. Most things don't take that long. What kind of optical activity is this? It's an optical activity that arises because you have the fibrils that are folding on themselves as they twist. And this creates heterogeneities along the light path. And these kinds of effects can be calculated. It's not very difficult, actually. You just need a matrix that describes the intrinsic properties of your refracting bodies. And then you need some orientation matrices because you might have more than one crystal lying on top of another. And then if you multiply all of these matrices together and then take the matrix logarithm, then you can separate out all the things that under ordinary circumstances are typically convolved. Here's another example. This is aspirin. Aspirin, you can see the crystals growing face on. They smoothly twist till they're edge on, and then they become face on again. And this is what the linear retardance looks like. Again, it's a 19th century micrograph. linear retardance is big and small and big and small and big and small. But if we can separate out the circular retardance, we see something that we wouldn't have expected. That every one of these radial bodies has a special plane. And that special plane bisects each one of these perfectly radial structures into a left-handed side and a right-handed side. Why is that? Well, it's because the first nucleus is centrosymmetric. It's achiral. But the crystal grows by a mechanism called small angle branching under high driving force, where each new crystal sends out some new crystals, but not in a precisely well-controlled crystallographic direction. And every crystal remembers whether its mother was the chiral face on the left side and consequently twists to make a right-handed helix, or whether its parent was the father on the right side, and all those subsequent crystals then twist in the opposite direction. And so you get beautiful heterochiral fields of crystals twisting in opposite directions, all determined by the symmetry of the proto-nucleus. And this is all a manifestation of how radial crystals grow under conditions of high driving force. This is Advil. It's just getting started. There's a left side, there's a right side. I showed you Advil, aspirin, and Tylenol. This is just a coincidence. It's not like we have any more pain in the lab than anybody else. It just is a coincidence that these were three good substances for doing these kinds of experiments. And so we wanted to see if we could build models of these ensembles that led to things that were polarimetrically comprehensible. And so we turned to the fur of the Angora goat. And here I'm going to embarrass myself because we heard such beautiful and sophisticated talk about textiles yesterday. But all we did was get some fur from a goat, and we just started twisting its hair in order to see what happened as models for ensembles of twisted crystals. And so Angora goat fur has a modest linear birefringence, and the fibers are pretty homogeneous. And so if we twist them to the right, if we twist them to the left, we can definitely see that this is manifest in their linear optical properties that manifest very clearly. If we take two fibers and tie them and wrap one around the other, we get structures that look like this. And ultimately, when we look at our ensembles of spontaneously crystallized things like aspirin, we recognize that these structures are braids of ribbons. They're really complex braids of ribbons, but they're braids of ribbons. And so is it possible to go from the microstructure of spontaneously crystallized things at high driving force through the theory of braids of twisted ribbons directly to things that we can measure in the laboratory, polarimetric observables? Braids are wonderful because they have a group structure. If you switch the strands with one another, they follow the axioms of a group. And if you then connect the strands from top to bottom in a braid, you can make various kinds of knots and links. And this is sort of a grand ambition, because we're starting here with something that is definitely twisted and definitely braided, but in a way that's kind of hard to articulate. We may be able to use the focused ion beam methods to really clearly see the topography of the objects that we're crystallizing. But you know, we can also examine Ride. You know, perhaps some people here are interested in topology because of the topology of DNA, circular DNA, which can be overwound or underwound, and the overwinding or underwinding leads to a ride which can compensate for the extra strain, which makes the linking and the twisting of the strands inequivalent. So if we take a fiber and we keep twisting and twisting and twisting like an old foam cord, it ultimately undergoes a ride like DNA, and you can clearly see that the ride then compensates for the twisting and the linking. And in this way, with goats, we are going to try to make crystal models of crystals. Yeah. So, yeah, crystals are more chiral than I ever thought. And they're getting more chiral all the time. And I'm happy to answer any questions.
Thank you for this wonderful lecture. So, questions?